Okay, today's topics, we're going to do two things. We're going to do properties of asymptotic bounds, and then we're going to take a little look at program correctness. Program correctness material should be a little bit of review for those of you who have had discrete structures, which is a co-requisite for this course. So anyway, so we'll start off with properties of asymptotic bounds. Now, let's review what we did in this chapter. We started by doing statement execution counts. By the way, speaking of statement execution counts with nested loops, I think we might want to spend some review time before the exam, because quite a few people, I put the solutions on the on the PDFs for you, but I think that's going to merit a little bit of a review. But at any rate, when we did this, one of the things that we found was that when we did a single loop, it was linear in n, and if we did a nested loop, it was what? It was quadratic, yeah. And what do you suppose would happen if you did a triply nested loop, a loop inside of a loop inside of a loop, and each index, each one was depended on n? It would be cubic, yeah. And then a quadruply nested loop would be to the fourth power, yeah. All right, is everybody clear? And then what we did is we did asymptotic analysis, and so we saw how to calculate. We defined big O, which is big O, upper bound or lower bound? Big O is upper bound. Yeah, O, I kind of think of O as over, So O is upper bound, omega is the other one, is the lower bound. And we saw how to calculate, and then what's big theta? If it's both what? Bounded above and bounded below, then it's big theta. And we saw how to do asymptotic analysis with polynomials. But now here's the thing. And then what we did is we looked at how to write a recurrence and how to solve a recurrence. And in these instances, what happens is you can get, when you do statement execution counts by solving the recurrence, you can get log base 2 behavior. So what we want to do now is we want to see how to do how all of these logs work. And so here in figure 3.9 is a figure that has a plot of three functions. It's kind of hard to see here on the overhead, but the x-axis is right here. It's below this one. It's kind of hard to see it. It's dim. I mean, the axes aren't shown. I should probably put a line there on. But can you see the x-axis? You see where it says 0 over there? That's the x-axis, right? And so what we have here is a plot of three functions. One is just constant at y equals 1. Are you with me? And when you were in algebra and you learned how to graph things, if you graphed f of x equals x, what would that be? Straight line, and it goes through, the y-intercept would be what? 0. Right? If you plot f of x equals x, the y-intercept is 0. Right? So that's linear, so there's n. And it's not at 45 degrees because the scale's a little bit different on the y as on the x. And now, did you guys, when you did college algebra or calc or whatever, you know what the graph of log n is. So this LG is log base 2, and what's the y-intercept of this? Trick question. Yeah, it's asymptotically goes down. And where does it cross the x-axis? At what? Okay, so the question is, at what value of n does log n cross the x-axis or the n-axis? It's 1, right? Because the log of 1 is what? 0. Is everybody clear? And you see how it's related to the function, to the constant 1 function and to the n function. Now from this figure, this is just basic plotting mathematics. From this figure, here we can note three things. first of all, if n is greater than or equal to 1, then the log base 2 of n is greater than what?
0.
How did you know? And you can see it here, right? Here's 1, and here's the 0. And so for n greater than or equal to, the log is greater than. For n greater than 1, greater than or equal to 1, the log of n is greater than or equal to 0. In other words, it's positive. Well, non-negative anyway. Are you with me on this? Okay, so that's fact number 1. And fact number 2 is that if n is greater than or equal to 2, then what? See, here's n equals 2. So if n is greater than or equal to 2, then what? The log of n is what? Greater than or equal to 1. So it's bigger than the 1 constant. Are you with me? And now the third one is, what about n compared to log n? What do you think? What about the n? So here we are comparing n with 0. Here we are comparing n with log n. What about the comparison of, we're comparing n with 1. What about if we compare n with log n?
It's always.
Yeah, it's always. Yeah, it's always. Are you with me? Now this you really have to see. I mean, we really have to, we have to understand that log n, so which is better, log n or n? Which is better, log n behavior or n behavior, linear behavior? Log n is better. Are you right? I mean, are you with me? So log n is better than n. All right? So now, here's the thing. You can use these facts then, if you have an expression and you want to prove a big O or a big omega, these are the facts that you can use to prove that it's big O or big omega. So let's do an example. So let's suppose that you have this f dot n is 3n squared plus 2n log n. And we want to prove that this equals big O of n squared. So what do we mean? Is it bounded above or bounded below? It's bounded above by n squared. All right, so what's our famous sentence that we have to write down? Must prove positive, what do you call them? C and not such that what?
F dot n.
Yeah, in this case, such that, what is our? 3n squared plus 2n log n is what?
Greater than or equal to Cn.
Greater than or equal to or less than or equal to?
Less.
Oh, the n squared is big O, so that's an upper bound.
Right.
So here, so it's less than or equal to. So we must prove that there exists positive constants C and n naught such that f dot n, which is 3n squared plus 2n log n, is less than or equal to Cn squared for n greater than or equal to n naught. But now look, you guys, see this has a log n in it, right? Now how do we always prove these? We start with which side? It's left side, and then we try to get all these terms we try to get rid of them. Now, just
Sorry.
all aha moments are gratefully acknowledged. So what do we try? So what can we do? Does anybody see what now? So we have to get this to be less than or equal to something. Can we just drop the 2n log n? Yes or no? Can we just drop it and say, oh, remove a positive value? No, because we're trying to get it. Yeah, we're trying to get this to be less than or equal to. So what can you see now with that knowledge that we have? Replace yeah with one that's exactly. So we replace log n with the larger value, and the larger value that we're going to replace it with is what? N. Now you see how that works? So 3n squared plus 2, and now do some what?
5n squared.
Do some math. 5n squared, and now what? Provided c equals 5. This equals what? Cn squared, and so actually that's a good question. What is n not going to be? Because is this going to be one where it's 1, or is this going to be one where any number will, any value will do? Because in order for this to be true, what has to happen? Log n has to be what? No, sorry. N, in order for n to be greater than log n. What was that? What was that? For n, let's go back to here. For n, for all positive values. So there's no restriction. This is true for all positive values of n, right?
But it
I was
has to be
saying 0.
negative, so it would have to be 1. It can't be negative.
Well, no. N is always non-negative. Right, because n naught is positive. It's more than that. It's always positive because n naught is a positive constant. So I think, according to this third one, it's for any value of n, right? So c equals 5 and any positive n naught is possible. Say n naught equals 1. Because see, we didn't use that. We didn't need that proviso, and we didn't need the proviso that it's bigger than 1 or greater.
Can you use any value and not after that?
Yeah, if there's no restriction, then as long as it's positive, you could say n naught equals 10. There it exists, and blah blah blah. But by convention, we always pick 1. Does everybody see? Now, I don't think I have it on the slides here, but if you, how could you show? Let's just do it in our head. How could you show that it's big omega? You would have to drop what kind of a? But the only time that can be positive, now n is positive, but the only time you can drop a positive constant is if what? Log n has to be what? It has to be positive. So you see, look. Yeah. See, so log n would have to be positive. Let's go back here. So what we're saying is that log n would have to be positive. So where is the log n positive? It's at 1. So that one would, see, so you have to be just a little careful to be precise. But anyway, that's how you do that. Now here comes something that you really, this has to become intuitive. We have to learn that, we have to be so familiar with this that it becomes very intuitive. This is going to crop up again and again when we look at these different algorithms. This, in figure 3.10a, is a plot of several different functions of n. And it's plotted with the n-axis going from 0 to about 15 or so, and with the vertical scale from 0 to about 40. And what we have here, the best one of all is 1. So that, can you tell, that's perfectly horizontal, and it's the y-intercept is 1, right? And you can see this log n. Now, because the scale goes all the way to 40, you can see this kind of, you can see that it's the same shape as before, it's just a different scale, but you see it's curving down. And then here's n. So do you see that log n is better than 1, but it's worse than n? So it's in between these two. Are you with me? It's in between these. Now there are some crossover points down here, a bunch of them we can see. But generally this is between this and this. Now what about n squared? Where's n squared? N squared's up here, right? Up here. So and this, and so if you look at that, that's the shape of a parabola, right? Is everybody clear? So that's the shape of a parabola. But now look, if n is here and n squared is here, what's in between n and n squared? See, this is n times n squared is n times n, but this one is what? In between is what? N times log n. So do you see that n times log n is the one that's in between n and n squared? And there might be some crossover points where it might not be, but for large enough n, that's true. And then here, let's carry it one step further. What about what's bigger than n squared? Well, n cubed is cubic, right? But what's between n squared and n cubed? Well, n times what? N squared times log n. And you can see that that's in between. Does everybody see how that works? So that's how they progress in order of increasing complexity. Yeah. Oh, sorry. If I said better than 1, then I misspoke.
I could have heard you wrong too.
Well, I could have misspoken. Unfortunately, it's on, it's recorded, so we'll see. So let me say it correctly. Log n is worse than 1, but better than n. Yeah, I might have misspoken. Okay, are we good with this? And then, of course, what's n cubed? What's between n cubed and n to the fourth? Log n, yeah. And so, and on and on and on. But now here we have a couple of other ones that are interesting. Notice here that there is a 2 to the n. All right? Now, 2 to the n is not quadratic. These other ones are polynomial. These other ones, these n squares and n cubes and n to the fourth, the pure n squares, n cubes, those are polynomial. Right? But this 2 to the n is exponential. And the other one that we have here is n factorial. You can see that one. Now, on this scale, it looks like 2 to the n is, maybe 2 to the n is better than what? Maybe n squared log n. It looks like it's better than n cubed. You know? But watch this. If you do this scale from, instead of doing from 0 to 40, if you do this scale from 0 to 4,000, then you can see these crossover points. See, there's a crossover point way up there that was out of our sight. But now when we compress the scale down, look at this crossover point right. This is an interesting crossover point because look. So now see, you can see that 2 to the n is much worse than n cubed, even though down here on this side of the crossover point it's not. See, so that was a little misleading because we hadn't hit the crossover point. And look at this crossover point, you guys. What is 10 cubed? 1,000. What is 2 to the 10? 2, 4, 8, 16, 32, 64, 128, 256, 512, 1,024, roughly 1,000. You see that crossover point there? That's like 1,000. You see, that's a, all right? And of course, what would happen is, on this scale, we could probably find like an n to the 50, and it would look like n to the 50 was worse than this. But, I mean, I don't know if it would or not, but if we compress it down and get the crossover point, ultimately what's going to happen? This 2 to the n is going to be what? Compared to any polynomial? Worse. And furthermore, what about factorial? That's even worse than exponential. Yeah.
What if you had like 10 to the n? Did that at every point like get
10 to the n is the same as, it's like 2 to, yeah, that's also exponential. 10 to the n is just a different base.
Does that ever get worse than n factorial?
No. Factorial will always, yeah. Yeah, now does everybody see this? This we have to have in our DNA. With this we need to know how these all compare. Okay, and now here, I think somebody asked this the other day about, somebody said, is big O the upper bound? And I was saying, no, big O is it's a set of functions. Now here in figure 3.11a, what I have here is a Venn diagram of the actual sets. So look, if you look at this inner oval, that says big O of n. Now, what is big O? Big O is a set of functions. And what are the functions that are inside that set? Those are the functions that are bounded what? Above or below by n? That are bounded above by n. Now, you got to get this. They are bounded above. Do you see that 2n plus 5 is bounded above by n? Are you with me?
Oh, yeah.
You could see, because you could find a constant, positive constant c and n, not such a blah, blah, right? And furthermore, what about 6 log n? Is that bounded above by n?
Yes.
Yeah, because we just saw that it's, you know, we just looked at them and looked at the crossover points. Are you with me? And look at this, and now this second oval are the functions that are big O of n log n, right? So now tell me, is 2n plus 5 big O of n log n? In other words, is 2n plus 5 bounded above by n log n?
Yes.
Yes, because it's linear. So for sure it's bounded above by n log n, because n log n is worse than n. Are you with me? So 2n plus 5, and not only is it bounded above by n, it's also bounded above by big O of n, but it's also bounded above by n log n, right? And also 3n log n plus 5n, is that bounded above by n log n? Yes, why is that? That's because the 5n there is added to 3n log n, and if n log n is bounded above, then n is bounded above, so you should be able to prove that. But we can sort of prove that in our head now, right? Is everybody with me on this? Okay, and how about the 17n log n? Yeah, that's just like a constant n log n, so, right? And then what happens is, this 2n squared plus 7n, that is not bounded above by big O of n, by n, and it's also not bounded above by n log n. Why not? Because n squared is worse than n log n. And of course, 1/2 n factorial. Doesn't matter if it was 1/billionth of n factorial. It would still not be bounded above by n log n. Now, does everybody see how these are placed? And do you see this shows that these are actually sets of functions. But look, what we can do with big O, we can also do with what? Big omega. So part B of this figure shows the sets of functions that are bounded what? Above or below? Are bounded below. All right? So look, is 1/2 n factorial bounded below by n log n? So here, see the big omega of n log n, these are the functions that are bounded below. So it's bounded below. All right? And 3n log n plus 5n is also bounded below, right? And then, but then 2n plus 5 is not bounded below by n log n, but it is bounded below by n, as is 9n minus 18. But it's not inside the, but why isn't the 2n plus 5 inside the small one?
Well, does it?
Why, let's make sure. Why isn't this 2n plus 5 inside this smaller oval? Why not?
It's not bounded below by.
Because 2n plus 5, which is linear, is not bounded below by n log n, because n log n is going to...
Is it bounded above by n log n?
Oh, well, the question is it bounded above by n log n? Did we do that one before? I don't know if I've repeated that one on this. But anyway, the answer is yes. Now, does everybody see how to place these? And then here's this constant 830. It's not bounded below by n log n. It's not bounded below by n. Now, does everybody see how to place these? This gives you a visual picture of what these sets of functions are when we talk about big O and big omega. Okay, and now, you guys, the last slide in this series are these asymptotic orders. And here, you guys, I don't know if you remember this, but you saw this in discrete structures. But now, do you see that these big O's are sets?
Yeah.
And what is this horseshoe symbol? What is this over here? Big O is a what?
Element of?
No.
Subset?
What kind of subset? Proper subset. Remember that? A subset, well, you'd have another line here. So big O of 1 is a proper subset of big O of log n. What does that mean? That means that there are some things that are bounded above by 1, or everything that is bounded above by 1 is bounded above by what? Log n. So this set is smaller than this set. It has fewer elements in it. Is everybody clear?
Which one is the smaller one?
Haha. It's big O of 1 is smaller than this one. It is a proper subset. Okay. Well. Okay. Look. This string of proper subsets is exactly is depicting this. What it's saying is that this set is a subset. This is a proper. Look. Big O of n is a what? Proper subset of what? Big O of n log n. That's all it's saying. You see? Big O of n is a proper subset of big O of n log n.
So then.
And it works on each little.
So would you interpret?
Okay, yeah. Let's say it like this. If it's in big O of 1, it is what? It must be in big O of log n. right? If it's bounded above by 1, for sure it's bounded above by something that's more. Does everybody see? So this is the set, these are sets of functions, and this is how to interpret it. And then you have the same thing going the other way for the, but this, you know, this sequence, we need to, all computer science people know this sequence intuitively. It's 1, and then log n, and then n log n, and then n squared, and then n squared log n, and then n cubed, and then n cubed log n, and then n to the 4th, blah, 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 and then 2 to the n, and then factorial. Okay? Because these are the common ones. These are the common bounds in a lot of the common algorithms. Are we good? Okay, and now the second topic for today is program correctness. Now, here's the thing. Everything that we've done up until now, what we are developing is we are developing tools to analyze how well these algorithms and data structures perform. So we're talking about how fast they perform. But what good does it do to have a program that performs fast if it doesn't perform correctly? Yeah, a really fast program gives you the wrong answer. Oh well. You know? So the thing of it is that we really concentrated on developing tools for program correctness in the discrete structures course. And we are going to use these tools occasionally in this course, but unfortunately time does not permit us to do proofs of program correctness for every algorithm that we investigate and implement. But we will do it occasionally, all right? And you should always, a good data structures book or a good algorithms book will have a proof for every algorithm, all right? So, but I wish we had more, I really wish we had more time, but we don't. So what we're going to do here then is we're going to shift gears and we're going to talk about program correctness. And furthermore, there's two basic situations where we have to prove program correctness. Now, in the same way that there were two situations for counting loop, doing statement execution counts, for loops we can actually go through and do this, count them up explicitly, and then for recursive algorithms we have to use recurrences, write down the recurrence and then solve the recurrence. It's the same kind of thing with program correctness. To prove iterative algorithms, algorithms that have loops, the key concept here is to analyze what is called the loop invariant. And this we did in discrete structures. And so we're going to review that now. And then the second situation, the second scenario, is to prove recursive algorithms. And, what we're going to do, because our time is limited, and we do prove recursive algorithms in the programming paradigms course, we're not going to, the materials in the book is in the manuscript and you can look at that if you want to, but we're not going to have time to prove recursive algorithms in this course. Yeah. So the question was, does that mean we only have to be responsible for iterative algorithms in this course? And the answer is yes. Okay? And even here, we are only going to do it occasionally. So the performance one, we're going to do that all the time. But for the correctness proofs, with algorithms that have loops in them, we're only going to do it occasionally. So if you're a little shaky on it, you might be able to, get through without too much damage. All right. Now, do you guys? We did this in discrete structures. You remember the 4 steps? Remember we had for loops. Does this look familiar? Okay. So remember there was a 4-step process to prove that a loop was correct. Okay. So first we prove that the invariant. Well, we have to identify the invariant. And then the first thing to do is to prove that the invariant is true at the beginning of the loop. So we had some initialization code, and then we established the loop invariant, right? And then we had to prove that the invariant is maintained with each execution of the loop, right? And then we had to prove that the loop terminates, because if it terminates, what good does it do to, it can't stop and give us the results if it doesn't terminate. So we had to prove that the loop terminates. And then we had to prove that the post condition holds at the end of the loop. Now, in the discrete structures course, we did this all very formally. Well, I think one of these was kind of informal. You remember which one? We had kind of like a verbal explanation. Yeah, you're right. It was, when we proved that the loop terminates, we usually did that. That was usually in the English informal argument. And the thing of it is that to set up all the formal machinery for this, because we're only going to do it a limited number of times, it's going to be a little less formal than we did in formal methods. So what we're going to do now is we're going to do this, we're going to prove this, the correctness of a loop by way of this same example that we did before. So the example is, does this look familiar? The example is what? Finding,
Finds the max.
yes, the purpose of this is to find the index of the maximum value in the array between, no. J gets one, it was between what? I think it's between 0, right? Well, let's think this through.
Oh, yeah.
It's between 0, right? I mean, we don't compare the one at 0 with another one because there's only, we start by comparing the first one with, let's make sure we got this. It says index of max gets 0. So that's the initialization, you remember that? And then we're saying what? So we start by comparing at 1 with 0 and then 2 with the max and so on. Right? And it goes up to, and what's the last one that we compare? Length minus 1. Is everybody clear? Okay. And so now here is a little, this is from a previous figure in the chapter. This is a little excerpt from figure 3.1. It's parts F, G, H, and I. All right? And so let's remember this scenario. Let's take a look at F, part F. Now you remember we said in this code, in this figure rather, this M stands for what in the code? What is this M? Yeah, this is index of max. I don't want to have to write it all out. So that's that. Are you with me? Okay, so that's that index of max. J corresponds to J, and I think that's the only abbreviations we used, right? Yeah. Okay, so this picture at F is the situation where we just did J++, and as a result of, after the J++, J, what's the value of J here?
85.
No, J is not 85.
30.
J is 3. A sub J is 85. Are we good? Okay, so, all right. And furthermore, at this point in the code, at this point in the code, M is pointing to what? Or what is the value of M?
2.
The value of M is 2, and A sub M is 70, and 70 is the what?
Max.
Well,
The max.
the maximum, not of the whole thing, but what? The maximum so far. Are you with me? The maximum so far. Right? And then what this code does is when it does, so let me see, J is 3. So then what it does is it says if A sub index of max is less than A sub J. So is that true? Is the if statement, is the if statement true? A sub M is less than A sub J? It is true. So what happens? Index of max gets J, so there's M gets J. Are you with me? And then J++. And now here it is at the end, at here. But now here, on this case, in going from H to I, what happened?
Nothing.
Well, something, yeah, you're right. Well, the test happened. The test happened, right? But index of max is what? A sub index of max is 85, and then A sub J is 40, 85 wasn't greater. So we just did J++, right? Now here's my question, you guys. To prove that this is correct, now if you can do this, this will be really good. What is the loop invariant after each J++? What is true at F and at H and at I? What is true at F and at H and at I. Well, that's true. There are lots of, it is true that M is less than or equal to J, and there are lots of things that are true. It's also true at this point that the blackboard is white, that the board is white, but what is the invariant that is most helpful?
J is less than length.
Well, that's also true, but that doesn't help us. That doesn't help us prove that it's correct.
Is it that J is
max from 0 to J?
Yeah, say it again.
Is the max from 0 to J?
Yes, M is not the max, but what? A sub M is the max of what?
A to J minus 1.
Of what?
0 to J.
Well, how do we say it? How do we write that? Look, how do we write it? Look. How do we write down the loop invariant? This is the hardest part, writing down the loop invariant, determining the loop invariant. How do we write down the loop invariant? What is true? Now, keep going.
I'm forgetting like how to say like.
How to say what? Keep going.
Okay, so.
Forgetting how to
max
say.
From 0 to J.
Well, what is max? Okay, so here's M.
For all.
And so for all, somebody say for all? Oh, good. Okay, yeah, so for all what is true? For all, don't say elements.
For all A sub I.
No, not for all. For all I,
range 0,
range what?
Well,
0 to J?
yeah. 0 less than equal I less
Minus
than
1.
J.
Well, either less than or equal to J, or, sorry,
Less than J.
less than J or less than or equal to J minus 1, but let's say less than J. So for all of these elements, what is true?
A sub M is greater than
A sub M, very
Well-
good, huh?
Okay.
yes.
Yeah, I think you're right. For all I, 0 in the range, 0 less than or equal to I less than J, A sub what? A sub M is greater than or equal to A sub I. For all of these I's. Now, you should know, this should make sense. Because this is the loop invariant. This is the useful loop invariant. Right? And it says what's true between here and here. So how do we prove that this loop is true? We establish that this invariant is true at the beginning of the loop. We make sure that it's true each time through the loop. We make sure the loop executes. And then we make sure that this satisfies the post condition, which is that for all of them, it's the greater. Right? So let's do each one of those 4. Yeah, this is good. I see the cobwebs being swept away. Okay. So here, let index of max gets 0, for int j gets 1, j less than length, j plus plus. If a sub index of max is less than a sub j, then index of max gets j, etc. And here we have written a sub I, the invariant. Okay. Now what was the first one? The first step was what?
Prove initialization.
The invariant is true at the beginning of the loop. Okay, now here comes the cobwebs really being swept away. All right? So what we're going to do is we're going to start with the invariant. So that's for all I, 0 less than or equal to I less than j. Body, a sub m is greater than or equal to a sub I. And this equals by the assignment statement. Now, so what is the assignment statement?
The beginning.
At the beginning, before because we want at the beginning, after the initialization. The assignment statement is what? Index of max gets 0. All right, and then it's for int j gets what? 1. So do you see then that from that code that gets executed, what does that do to our invariant? What should we plug in? What should we plug into there?
0 and 1.
0 for what?
For M.
For m, and what?
J.
1,
J.
1 for j. Now, are we good? Is that good? So here, okay, so that becomes 0 less than or equal to I less than 1, a sub I, or sorry, a sub 0 is greater than or equal to a sub I. Okay. And now, what about this 0 is less than or equal to I is less than 1?
It just becomes zero.
I equals 0.
Do you see that that's mathematically equivalent to what? Somebody did say it right.
I equals 0.
It's mathematically equivalent to I equals 0. So by math, 0 is less than or equal to I is less than 1. The only way that can be true is if I equals 0. Right? So that equivales that. So we're going to put this in. But now you guys who took discrete structures, formal methods, what do you notice? Excellente!
In the class right now.
Oh, you're in the class right now? Yeah, this is, do you remember the one-point rule? When you have equals in the range, it's the one, and what's the rule? So here, how did the one-point rule work? What do? You put, yeah, but how do you compute? What do? You take the body, right? Yes. The textual substitution of when it's I equals 0. So you textual substitute, replace, into the body. Right? Oh, good. Excellent. So it's A sub 0 is greater than or equal to A sub 0. But look. Yeah, that's by math, right? That's something is equal to itself, so that's true. So the invariant is true at the beginning of the loop. Yeah.
So we're getting this equal true, not imply true.
Right. After all, if we got it to imply true, we wouldn't be proving anything because everything implies true. See? You can get it to follow from true. If you can get an expression to follow from true, then you have proved it. But if you get it to imply true, you haven't proved anything. That was a good question, and more cobwebs. Yeah. Okay? Now, the next thing we're going to do is informally. The invariant is maintained with each execution of the loop. So now what happens is we have to look at, oh, by the way, I just updated this, there was a typo. So if you're getting these slides online, you better refresh your browser. Okay? So now, there are two cases. What we have to show is that this invariant is true in these two cases. In the case where A sub m is greater than or equal to A sub j, in which case does the if statement, does the body of the if execute? Case 1, does the body of the if execute? Yes or no? Case 1, does the body of the if execute? Yes or no? No, because it says the guard is if A index A sub m is less than A sub j, that's when it executes. So if A sub m is greater than or equal to A sub j, it doesn't. Case 2 is if it does. So here, I'm not going to write it all out, but I think we can just go back to here, figure 3.12, and see what happens. Because look, if A sub m is greater than or equal to A sub j, what happens is the only thing that happens is that j goes up by 1, right? So if j goes up by 1, this element now is in this region, right? But the thing of it is that in that case, this element here is not greater than m. So if m is greater, it's not greater than m, but if m is greater than all the other ones, and this is not greater than that, then A sub m is still greater than all the other ones. Are you with me? It actually also depends on transitivity. The other case is if this element is bigger than m and you move it over 1, this element is guaranteed to be bigger than all the other ones. Why? Because this one is bigger than m and m is bigger than the other ones, therefore this one is bigger than the other ones. So see, it's kind of like transitivity. So anyway, you'd have to write all that out to do it.
Do we write it formally? Or?
No, I didn't even, I mean, this English argument is in the text. This English argument is in the text. And now, how can we prove that it terminates? Well, j starts off to be what? 1, so that's got to be, so the length can't be less than 1 for there to be a maximum. And each time through the loop, what happens?
It increases the
it increases by 1, and no other statements in the loop change the value of j, so eventually it must do what?
Execute.
Or equal.
Equal length,
Yeah.
right? In which case it terminates. And now for the post condition, this is the post condition. The post condition is that in the end, 0 has to be less than or equal to m, which has to be less than L, so L is length. And now, do you agree that this is the proper post condition for this algorithm? For all I 0 less than or equal to I less than L, the length, A sub m is greater than or equal to A sub I for all those. That's at the end. So that's all you have to do is write down, starting with the invariant, you just write that down. And then you say the final value of j. You know, in the end, what's the final value of j? It keeps going up, 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 and then finally when it breaks out of the loop, it's what? It's one more, so it's L. So you plug in what? You plug in L, and that is that post condition. All right? There's two parts. There's that part, and then there's two conjuncts. The second conjunct is what we just proved, and the first conjunct holds because m is initialized to 0. That is that m has to be less than or equal greater. That is that 0 is less than or equal to m, which in turn is less than L. And this is true because m is initialized to 0. And the only statement that can change m is in the assignment statement, index of max gets j. Right? And the guard on the for statement, j less than length, you know, guarantees that the assignment happens only when j is less than L. So anyway. So like I said, we're not going to, there's material in the manuscript for proving recursive algorithms. We're not going to do that in this class. And I think your assignment statement for tomorrow is your last pure written assignment, which is this material we just did. And so I'll see you tomorrow. All right.